Okay, alright, I believe we are live. Let me just make sure that the audio is working. Just give me a second for it to come up, please. Okay. Yeah, alright, so it looks like we're live. Welcome back, ladies and gentlemen, to another physics lecture review. I have not shaved. I'm wearing my glasses, so I woke up super late today, which is basically how it goes. It's a Sunday. I'm gonna do another lecture review. I think I'm gonna do 2 of them today because I'm a little bit behind. But let's just, first of all, let me jump right into it and give a brief overview of what we're gonna do. This is kind of a continuation of last video. We're just gonna be looking at 2 more momentum problems, maybe 3 more, and it'll be fun. It's gonna be a relatively shorter video. So, okay, so let's just dive into it. I'm gonna hide my face because it's hideous. Nah, I'm just kidding. And yeah, let's just make sure that everything's working. You guys can see what I'm writing on all 4 corners. So yeah, funny enough, there seems to be like some extra space over here and over here that I can't write on, but you guys can still see it. It's actually a little bit weird. Not sure how I feel about that, but whatever. It's not that big of a deal. So let's just hide everything and let yeah. I guess you'll just see some of the previous page. I'm gonna be writing over here. Okay. All right. Let's zoom in here a little bit. Yeah, I like that. Okay. All right, let us dive right in. So, last video, I actually ended a problem before I had finished the problem. And so, because we hadn't finished it in class apparently, I didn't realize that. So let's just go through that problem again. So, the problem is as follows. Imagine you have a rocket of some kind. So let's draw a rocket. This is a rocket. It's got its little fins, I suppose. And the rocket is shooting out fuel. Okay. Some information at time t. That's not how that works. Beautiful. At time t, that looks terrible. Okay. The rocket plus the fuel is moving at a certain velocity. So like this over here is the fuel, and imagine the fuel is still inside the rocket. I guess they're both moving together. So actually, I'll take this arrow away and let's just put the fuel right up against the rocket, basically. Okay, so at time t, rocket and fuel. That's not how you spell fuel. How do you spell fuel? There's an E over there. Fuel moving with. I'm gonna zoom out a little bit. I don't like this. Moving with velocity v. Okay, simple enough. So at time t, the rocket and the fuel are moving at it with a certain velocity v. Okay, and let's just say, okay, so that's the information we want to find. Yeah, find acceleration. Find acceleration. Find the function for acceleration in terms of dm over dt. In other words, in terms of the amount of fuel that's being shot out of the rocket at every moment in time. Okay? Like the amount of, so it's not find a of t, it's find a of dm over dt. Okay? Oh, and this is actually important. We could think about this, since we know the velocity, we know that the momentum of the rocket and the fuel, so p equals the velocity, right? Times, what is it times? Well, it's times the mass of the rocket and the fuel that's in the rocket plus delta m. And this delta m is an interesting idea. You could think about it in terms of delta m. Delta m is the small amount of fuel that's about to be shot out of the rocket, right? So the momentum is the velocity times the mass of the rocket plus delta m. Okay, and we want to find acceleration in terms of dm over dt. Okay, so some more information. Fuel flies. I don't know how to spell, guys. I really don't know how to spell. Flies out with velocity u. Okay, some more information. So when the fuel flies out, it's flying out with some velocity u with respect to the rocket. With respect to rocket. That's important, that it's with respect to the rocket. Why? because this is not with respect to the origin. It's not like the fuel has some true velocity u. It's more that the fuel has some not true velocity u with respect to the rocket. So if the rocket is moving at 5 miles per hour, 5 meters per second, and we say that the fuel has a velocity of -3 meters per second with respect to the rocket, then you could think that the fuel has a velocity of no, then you could think that the fuel has a velocity of 2 meters per second. It's going 3 meters per second slower than the rocket. Yeah, basically the rocket sees itself as the origin, and it's accelerating though. But anyway, the point is that the u is with respect to the rocket, not with respect to our stable origin that we'll create. Like, we'll create a stable origin. The rocket is like over here, and it's accelerating in some direction. And the mass has some true velocity, but from the point of view of the rocket, I guess, let's see, this is, from the point of view of the rocket, that true velocity would look something like this, I guess. Yeah, like that. Like very intense flying away from the rocket, if the rocket was to view itself as stationary. So the point is, we need to find the true velocity, because u will not serve as our true velocity. U is the velocity of the fuel with respect to the rocket. That's important. Okay. Any more information that we need? No, I don't think so. I don't think so. So we're trying to find the acceleration of the rocket. Okay. So let's just say, let's just make a few things to help us out. Let Vf of the rocket, let Vf of rocket equal v. Remember, v is the velocity that we gave the rocket at the beginning. V plus delta v, like plus whatever it changed. That's that's a basic definition of velocity. V plus delta v. This is just going to help us write things out. So that's something that we should make. And then let's say that well, we have to find the velocity of the fuel in the lab frame, in the true reference frame. So let's figure out how we're going to do that. Okay, so let's consider 2 dimensions, right? Just 2 dimensions. Imagine that the rocket is over here, and it has a position of big R, and imagine that the fuel is over here, and it has a position of little r. And the position of the fuel with respect to the rocket is, let's say, little r prime. Yeah? So now, if we were to take the derivative of all of these, we get that the velocity of the rocket, v, v plus, what is the derivative of r prime? Well, the derivative of r prime is the rate at which the fuel is being distant from the rocket. It's the velocity of the fuel with respect to the rocket. Okay, well, we know that. That's u, right? Oh, let's write this out clearly. So in terms of position, r plus r prime equals little r, right? R plus, yeah, as vector addition shows us. So then, because of that, we know that v plus u equals, I don't know, what should we call this? I don't know what to call this. Let's just call this VF. No, VF, it means something. It's like, V plus U. Oh, actually, hold on, it's not V plus U. We're looking at this after... We're looking at this after the fuel has left the rocket, so it's V plus delta V, right? Because that's what we showed over here, the final velocity of the rocket. So it's V plus the delta V plus U. That's the velocity of the fuel. For now, I'm just going to call this V fuel. Right? Simple enough. Okay, so we got the velocity of the fuel. That's excellent. Let's bring this guy up here. And yeah, I'll leave this. I'll leave this over here. Okay, that's how we got the velocity of the fuel. We just took a look at the positions, and then we found out how the positions related to each other, and then we took the derivative of all that. Okay, so now let's write down some things that we know. We'll use momentum as our thing. We know that there are no outside forces on this thing, so we know conservation of momentum has to be a thing. So let's take a look at what momentum is at these 2 different moments in time. Okay, so at time, so by the way, we found the momentum at the first instance of time. The first instance of time, the momentum is this, right? So we know that momentum. We know that momentum. It's PV m plus delta m, right? So now let's find the next momentum. So at time delta t, and again we're going to consider the rocket and the fuel as one entity, and we're going to find the momentum of that one entity, the net momentum of that one entity, because we're viewing them as one closed system of particles. So at time delta t, the momentum of this system that we're looking at, the momentum of t plus delta t, sorry, it's not at time delta t, it's at time t plus delta t, my bad, t plus delta t. So p of t plus delta t equals the mass of the rocket, right? The mass of the rocket plus whatever fuel is still left in the rocket, times the velocity of the rocket, which is v plus delta v. Okay, and then plus, now we need the momentum of the fuel. Well, the momentum of the fuel, it has a mass. We gave it a mass. The mass is delta m. And then what's its velocity? Well, we found its velocity. We found its velocity over here, right? V plus delta v plus u. V plus delta v plus u. Right? Beautiful. Beautiful. Big fan. Big fan. All right, so now we have the two momentums, and we could get the net momentum. We could get delta p. Okay? And this will all make sense why we're doing this in a second. Delta p equals p of t plus delta t, and this should be a vector, minus p of t. Okay, well, let's just set that up. This equals m times v plus delta v. Someone's calling me, I think. Oh, my brother's calling me. Give me a second. I will answer this. Hey, what's up? I'm good. I'm in the middle of recording a physics video. Oh, okay. He said one second. I'm in the middle of recording a physics video at the moment for YouTube. So can I call you back later? Great. Thanks. Bye. Super cool, dude. Now that phone call is timeless on the internet. It's beautiful. Yeah, I'm helping him with something. I'm trying to learn something to help him with something. I hope I can do it. But anyway, moving on to physics. Let's have that face. Okay, so we have p of t plus delta t minus p of t. So we have m times v plus delta v plus delta m. You know what? Actually, since we're gonna have things canceling, let's just write this in a more helpful manner already. So we're gonna have m times v plus m times delta v plus delta m times v, delta m times v, plus delta m times delta v plus delta m times u. Right? We just this was all p of t plus delta t. That's just all of this expanded, right? Okay, and then all of that minus what do we have up here? We had v times m plus v times delta m, so it's going to be minus m times v minus m times minus delta m times v. Yeah, minus delta m times v. Okay, now let's take a look at this this whole thing in all of its glory. So, let's see. M times v, these two will cancel, right? And then delta m times v, these two will cancel, right? So we'll be left with that the change in momentum, delta p, is equal to m times delta v, m dv, m times delta v, sorry, we're not doing the d's yet, plus delta m delta v, right? So that's the change. Okay, hold on. Plus delta m times delta v plus delta m times u plus delta m times u. And yeah, I think that's it. So great. So this is our delta p. Okay, now let us take the limit, the derivative, how would I say this? Well, if we were to if we divide all of these by delta t, like if we divide this side of the equation by delta t, and we divided this side of the equation by delta t, divided by delta t, divided by delta t, right? That's basically what I'm going to do. And then I'm going to take the limit as delta t approaches 0. So what will happen as delta t approaches 0? Well, we'll have dp over dt, the derivative of momentum with respect to time. And we're going to say that that equals m times dv over dt plus, this is interesting, delta m as delta t approaches 0, delta m also gets very, very small. And as delta t approaches 0, delta v also gets very, very small. And so when we'll basically have a very small quantity with a very small quantity, this will all just approach 0. As delta t approaches 0, this whole term is just going to approach 0. So we can literally just write that 0. Plus, we're going to have dm over dt times u. Okay? All right, so rewriting all of that, how much room do I have to the left of me? Oh, quite a bit. Okay, so rewriting all of that, we have that dp over dt equals dv over dt times, what was it, m? Yeah, times m. Sorry, I completely forgot my vector signs. Plus dm over dt times u. Sorry, and this should be a lowercase m, because it's the small amount of mass being ejected. Okay, so that's very interesting. We found the change in momentum. And this is where I think I left off last video, but there's more to do, because if we think for a moment, we'll realize that there are no external forces on the rocket, right? All that's happening to the rocket is it's expelling its fuel. And so since there are no external forces on this system, we know that the change in momentum has to equal 0. Right? There are no external forces, and therefore the change in momentum has to be 0. So that's very interesting. All of this is 0. Very cool. Very, very cool. Okay, well, if that's true, then let's find our acceleration in terms of dm over dt. Right? That's what we wanted to do. Okay, so let's restart all of this with our newfound information. Let's think some new ideas, which will be very useful. Given our newfound information, we know that, I'm just going to rewrite it, m times dv over dt plus dm over dt times u equals 0. Right? Very interesting. Very interesting indeed. And because of, okay, so there you go. That's one very important thing. Now let's think about this. Right. Okay, that's interesting. I guess when I wrote dm over dt, what I really want is the change in the mass of the rocket, not the small amount of fuel that's being checked out. So instead of writing dm over dt, let's just establish that dm, d little m over dt, the small amount of fuel being injected, is equal to negative d big M, the change in mass of the rocket over time. Right? It's just a negative of that. And so with that information, we write that that m times dv over dt minus d big M over dt times u equals 0. Right? Okay, and so therefore, we understand that dv over dt equals 1 over m times dm over dt times u. And here we go. This is the acceleration in terms of dm over dt. Very interesting. Very, very interesting. Now, oh, there's a comment. Hello, Happy Good. You were a jolly guy who lived, streamed game, and loved Harry Potter. How you changed from there to a PhD lecturer? I am not a PhD lecturer. I am just a dude. Hey, Suba. All right. Schrodinger's cat. Very funny. I think that's supposed to be Schrodinger's cat. Okay, so let's see. Where were we? Okay, so we found the change in velocity with respect to time, and sorry, not with respect to time. Crucially, we found the change in velocity with respect to the amount of fuel being shot out every second. And what's interesting is that the variable t is not here, right? Time does not play a factor. Your acceleration depends only on the amount of fuel you expel. It does not change at all about how fast you do it, right? That's interesting. Although, of course, it does depend on time a little bit because it's dm over dt, and so time is here a little bit. But whatever. Okay, now let's take this even a little bit further, shall we? Let's say that if we know that dv equals 1 over m times dm over dt times u, then this tells us, and here we're going to use something that we haven't used before, at least I think so, not on this stream at least. Here we are going to use something called an integral. The integral from the initial velocity to the final velocity times dv. Oh, and by the way, what I did is I just I removed the dt from both sides, I believe. So that equals, u is constant, so that does not have to go into the integral, u times the integral from the initial mass to the final mass times dm over m. Or more appropriate would be 1 over m times dm. Okay. This, because of integral laws, is simply going to be vf minus vi equals u times the natural log, I believe, times ln of the final mass divided by the initial mass. Okay? And so that's very interesting. So now we have a way of getting the velocities, right? We just integrated to get the velocities. And so because of this, with this new information, if vi is 0, so vi equals 0, if we're looking at just the first moment, then that means that the final velocity is going to equal u times ln of the final mass divided by the initial mass. That's super interesting, because time is truly not here. The velocity does not depend on time. It is solely based on the ratio of the final mass divided by the initial mass. I think that's fascinating. I think that is absolutely fascinating. And so let's think about this. The final mass, mf, as long as fuel is being ejected, mf is always going to be less than mi, right? And so that means that it's going to be the log of something greater than 1. The log of something less than 1. The log of something less than 1, but greater than 0, unless mf is truly 0. And whenever you have something like the log of x, where x is less than 1, sorry, this doesn't make any sense, ln of, where you have the log of x, where x is less than 1. And whenever you have something like that, that is less than 0. So this is going to be negative, which means that the final velocity is the opposite of u, like it's in the opposite direction of u, which makes a lot of sense, that when u goes off in this direction, the rocket goes off in this direction. And so the only thing here that's a vector is u, and this is just a scalar. And so u is being scaled by some negative quantity, and that is exactly what the final velocity is going to be. And in fact, the final velocity is going to be the sum of all the little u's. So the final velocity of the rocket is the sum of all the little u's. And that's super interesting, that's what we're talking about here. And it makes a lot of sense. It's very intuitive. Okay, beautiful. That was one problem. Oh my god, we started at the middle of the page. Why is that? I was wondering why the page felt so short. Okay, so you know that is one problem that we've done. Let's move on to the next problem for today. All right, and I will not let us go to the bottom of the page again. That was ridiculous. Okay, let's start. That's too far out. There you go. That's okay. Okay. So now let's talk about a case where time will matter. A case where time does factor into our situation. And that is when we have a rocket in a gravitational field. Okay? So let's establish something. That F in this situation, sorry, you know, let's put this thing further down. F equals, should it be negative or positive? Should it be negative or positive? I'm gonna make it negative. Negative mg. Okay, and here is our coordinate system. Right, so F equals negative mg, and we have a rocket. And to make this simple, let's just consider that the rocket is only going up. Sorry, that's a terrible rocket. There you go. Here's our rocket. The rocket is going up, and it is expelling fuel. Right? The fuel is going out with some velocity u, again, and the rocket is flying with some velocity v, again. V going up, and u going down. And u, again, is with respect to the rocket. Okay? So let's do this all again. Okay. So F, oh boy, F equals dp over dt, right? That follows from basic definition of momentum, which equals m times dv over dt, right? The acceleration of the rocket, minus, so mass times acceleration, minus dm over dt times u. dm over dt times u. And sorry, just to reiterate, this follows from what we had shown over here. Where is it? Dv over dt times dm over dt times u. Right? We just proved that over there, and we're just gonna use that over here. So it's this quantity. Right. Right. Yeah. So this is the change in momentum. And that equals our force, which is negative mg. And you see that u and g are going in the same direction, right? Negative mg. Okay. Okay. Yeah, and this is big M. This is the change in mass of our rocket. Wonderful. And so now we have a situation where we have that dv over dt, the acceleration, just like we had before, is equal to 1 over m times dm over dt times u, right? Over dt times u, minus g. And remember, we just divided by m, and that's why the m over here got canceled out, right? We took this, we brought it to this side, and then we divided by m, and so this got canceled, and we have a 1 over m over here, right? All that makes sense. And so now, let's find the velocity again. Let's find the velocity again. So again, we're going to take the integral. And so, yeah, so let's take the integral. So we have that. Where should I put the integral? So first of all, why are we all the way in the middle? I don't understand this. Everybody get to the side. And yeah, let's take the integral. So we have the integral, oh boy, the integral from vi to vf of dv equals the integral, actually no, because mass does have to go inside, so it's just going to be u on the outside. U is a constant. The integral of u from mi to mf of 1 over m times dm minus the integral of, actually g could go outside because g is a constant, g times the integral from, what will this be? I think ti to tf. Ti to tf times delta t. Why is delta t here? Again, because what we're doing is we're sort of treating these derivatives as fractions. And we're bringing the dt, so we're multiplying each side by dt. So this becomes df, this becomes 1 over dm times, 1 over m times dm times u, because the dt goes away, and this becomes g times dt. And so then we're taking the integral of all of those things. Then in the next video, I'll talk more about integrals, and we'll get a slightly better understanding, but honestly, even I don't really fully understand integrals yet. I didn't get up to there in my official math class. But I have a good enough understanding of them. And so because of the laws of of integrals, which I'm not going to talk about here, this becomes vf minus vi equals u, again it's u times the ln of mf over mi, of mf over mi, minus g times tf minus ti. And so already maybe you're seeing some of the rules. For example, that the integral of dx from xi to xf is simply xf minus xi. Right? That's one rule that we're seeing again and again. Okay. And okay, great. And so now let's set vi to 0. And vi will be 0 at ti is equal to 0. So vi equals 0 and ti equals 0. When that happens, let's just come over here. Actually, no, there's room. There's a lot of room. So when that happens, we get something that looks like this. We get vf minus vi, which is 0. So vf equals u times the ln of mf divided by mi. And mi, in this case, is probably going to be like the full mass of the rocket, right? Because we're talking about just the initial moment in time. Minus g times tf, which in this case will just be t. You could think of it as t. So velocity is equal to this. And so now look at this. This is super cool. T is here. And so basically this means that the shorter the t, in other words, the faster you expel out the fuel, then the faster, the higher VF will be in that moment of time, which is super interesting. Okay, so that's the end of that problem. It was pretty easy. It just introduced some integrals. We introduced some integrals today. We're going to talk more about integrals and how they make sense and what we use them for and why they're here in the next video. We're also going to introduce energy in the next video, so that's going to be super interesting. And yeah. So hope you guys enjoyed. Hope you enjoyed, learned something, all that jazz.